Alright, this is 2009 number 5. This is a great little question with not a lot of calculations, but covers a bunch of different little topics, and so I think it's really beneficial. Has a lot of thermochem in it. So here we go. It says, answer the following questions about the information related to reactions X, Y, and Z. They give us equations, and then they give us delta H's, delta S's, delta G's. This is a little summation equation. Z is from X and Y if we flip those guys and add them together. So we're going to see a piece of that along the way here. So here's 5a. It says for the reaction X, write the expression for the equilibrium constant Kp. Easy enough. So Kp equals, no brackets here, parentheses, solids don't play. So this is carbon monoxide gas pressure times hydrogen pressure, all divided by the water. That's it. They all happen to have coefficients of 1, and so we don't have to deal with any exponents there. So that's it. That's the Kp on 5a. Then B says, for the reaction X with the equilibrium constant Kp, will it increase, decrease, or remain the same if the temperature rises above 298? So these not symbols are all mean we're in standard conditions at 298 degrees or 298 Kelvin, and they're asking, will this reaction, if we increase the temperature, shift right or left, right? And so when we look at this, this is endothermic, which means that heat is on this side of the equation, that side of the equation. And so if we add heat, it's causing the equilibrium to shift across towards the product. So the answer is because it's endothermic, because reaction X is endothermic, an increase in temperature will cause the equilibrium to shift towards products and then answer the question. It says, will Kp increase or decrease? Therefore, Kp will increase. We'll have a greater number of products over reactants, so Kp should increase as a result. That's part B. You gotta talk about it's endothermic, and so adding temperature causes it to shift. Part C. Alright, we can still see it. For reaction Y at 298, the value of Kp greater than, less than, or equal to 1, justify your answer. So they're asking us for the Kp here. Is it bigger or less than 1? We have to, in order to figure out whether it's bigger than or less than 1, look at our delta G value. And so I'm looking at the delta G value in the chart. The delta G value gives free energy as positive. If it's positive, that means it's non-spontaneous. If it's non-spontaneous, it means reactants are favored. So for part C, the answer is Kp is less than 1. Because delta G is negative. And therefore the reaction is non-spontaneous reactants are favored and K is less than 1. That's it. It's determined by the delta G being non-spontaneous. You could come in here and put delta G equals negative rat link. That's a fair way to state that as well. In fact, you could also put that in that answer just to make sure you've covered all your bases. Part D says for reaction Y, which is larger, the total bond energy of the reactants or the total bond energy of the products? And explain it. We have a delta H for reaction Y is plus 41, so it's endothermic. And so I would write the equation out. I would put delta H for the reaction is equal to, this is the one time it's reactants minus products for Hess's law with bond energies. So I don't write reactants minus products, I write bonds broken minus delta H of bonds formed. I think that's a good start to the explanation for this problem. And so which one has to be bigger? Bond energies are all positive, so the broken bonds have to be bigger than the bonds formed, right? In order for that delta H overall to be positive. So the total bond energy of the reactants, let's answer the question. The total bond energy of the reactants, total bond energy for reactants must be larger for an endothermic reaction. And I would put, it takes more energy to break the reactant bonds than is released when product bonds are formed. That's how I'd answer that question. Total bond energy for reactants must be larger for an endothermic reaction. It takes more energy to break reactant bonds than is released when product bonds are formed. That's it on part D. We're cruising. Part E says, is the following statement true or false? Justify your answer. What a shame. It would be better if we didn't have to justify. We could just say, it's true. Call it a day. Is the following statement true or false? On the basis of the data in the table, it can be predicted that reaction Y will occur more rapidly than reaction X will occur. The answer is false, because we don't have any rate data. Is really the answer. You can't tell from thermochemical data any information about the rate of the reaction. That's it. All I can tell is whether the reaction is spontaneous or non-spontaneous. I can't tell anything about how fast or slow it goes. And this is really back to when you have these graphs, the part up here at the top, this part of the graph, that's rate. The bottom part here, that's thermo, right? From start to beginning is thermochem. The rate is all determined by the height of that peak, by the activation energy, and here we can't tell the activation energy from the thermo data. We have to go and do rate data to find how tall that hump is. That hump. Check it out. Good? And then the last piece of this, piece F, says consider the reaction Z at 298. Is delta S for the reaction positive, negative, or 0? Justify your answer. All right, so here we go. We have an equation. I always tell you, look at moles of gas. It is 2 moles of gas on this side, going to 1 mole of gas on the product side. So are we moving towards more or less disorder? Here we're moving towards less disorder. So they ask for the sign on delta S. Delta S is negative. Because we are moving from 2 moles of gas on the reactant side of the equation to 1 mole of gas on the products. Less disorder. Sorry, I think that was off the screen for a little bit. So delta S is negative because we're moving from 2 moles of gas on the reactant side to 1 mole of gas on the product side. There's less disorder there. That's it. That's F part 1. F part 2 asks us to calculate or determine the delta H for the reaction. And so on this guy, to determine the delta H, we have to look at these other reactions here. We need carbon monoxides on the reactant side. This is where the summation equation comes in. In order to find carbon monoxides on the reactant side, we have to flip both of these equations. We have to get those carbon monoxides over there. So we're going to flip both of these equations, and you'll see when we flip both of the equations, these guys all still cancel out, and we flip them, we get 2 carbon monoxides on the reactant side going to 1 carbon and 1 carbon dioxide. When we flip them, what happens to the delta H's? The sign also flips. So our delta H for Z is going to equal the negative 131 kilojoules per mole plus the negative 41 kilojoules per mole on the second reaction, and we get a delta H for Z of negative 172 kilojoules per mole. That's your answer to part 2 on F. And then part 3 on F says a sealed glass reaction vessel contains only carbon monoxide and a small amount of carbon. If the reaction occurs at the temperature and the temperature is held constant, will the pressure increase, decrease, or remain the same? If all we've got is carbon monoxide initially and carbon initially, which way does this reaction have to shift? That means that's 0. So the reaction has to shift to the right. So we are going to go from 2 moles of gas to 1 mole of gas. I would put reaction must move to the products side, and there are less moles of gas and less overall pressure. So the pressure is going to decrease. That's what they're asking. The pressure will decrease, less overall pressure at the end. Because we don't have any carbon dioxide, we know it shifts that direction. That's 2009, number 5.